Good afternoon. I'm just waiting for people to enter, and I don't see too many. I wanted to start where we left off. We're going to discuss inference on the mean. Okay? And as I explained last time, this is summarized in the formula sheet, row number 5. So we begin with the first column. First column is regarding confidence intervals. So using a sample, we can compute our best estimate, our best guess at the mean, which is the sample mean. So the best guess at the true mean is the sample mean. And then we can present, because of the theory, we know the sample mean is distributed normal with a, well, in this case we assume, right? So we're going to assume we don't know the mean. So this is inference on the true mean, where the true mean is unknown. However, sigma, the true standard deviation, is known, right? So we're going to take what we're going to do is take the best estimate, the best guess is the sample mean, and then we're going to say, well, we want to capture C percent, 95%, 98% of the observations around it and present this as our confidence interval. So to get like 98% around X bar, we want to go so many standard deviations from the mean. This is the standard deviation of X bar, remember, right? This is all from number 3. So the results of number 3 I use here. All right. So those problems ask you to solve for today. If not, we can step through a few of them. So I asked you to do questions 1, 2, and 3, at least 1 and 2 for today. So compute the confidence intervals for this example. A simple random sample of size 100 is taken from women in Canada in hopes of estimating the true average height. Mu. Of all women 18 years of age or older, the sample average is calculated to be 5 feet 4 inches or 64 inches. The standard deviation of actual height of women is known to be 2. So the sample result is here. Now this is really important that you distinguish between sample results. So this is X bar equals 64 and population results. So for some reason we happen to know the true standard deviation, but we don't know the true mean. The true standard deviation happens to be 2. We're not going to ask too many questions. We're just going to use these results and the formulas on row 5 to answer questions like this. So the 95% confidence interval of the true mean of women's heights is going to be X bar. Yeah, I'm going to make this bigger. So So it looks nice when I shrink it. So x bar plus or minus z star sigma over root n. So for the first part, for part A, I need, well, I have x bar, I have sigma, and I have n. Let's go back and see what n is. It was a sample of 100, so I'm going to write that down in my data. So sample was 100. Okay, so these are my bits of information. And plugging it all in, .64. Sorry, tapping the screen. 64 plus or minus for a 95% confidence interval. We need to pick that up. This is 2 and this is 100 with a square root. Don't forget that root. So I need to know what's z star. Z star, how many standard deviations do I have to be away from the mean to capture 95% of the observations? So we need to figure out from the standard normal distribution how many standard deviations away to catch 95. Well, we know that from the rule. It's like 2 or so, right? Let's do this. Z is equal to -2 and 2. So negative Z is -2 and positive Z is 2. Something like that. Well, that's just, remember those results of 2 standard deviations, that was what we learned in unit 2 a long time ago. But we want to be more precise than that, right? That was just an approximation, saying 95%. They were just rounding up. What precisely would give us 95 in the middle? Well, we did check that back in unit 2 norm. But the fastest way to get that number, or you can memorize it because we use this a lot, is find it available here on the bottom of the t distribution. Remember this? This is like the second last page of your notes. So it is going to be 1.96, very close to 2. Okay, so it's more precise to 3 decimal places on this table. So you would round it to 2, but we want more precision. So we're going to use 1.96. So going back to what I was doing. Oops. I wonder if I can type the number somewhere. Page number. I think it's here. 20. All right, so we're going to use 1.96. So we're going to update that table. And in fact, for 3 decimal places, it's negative Z, and Z is negative 1.96 and positive 1.96. Okay? So, that's what we're going to put here, 1.96 times this. That didn't work. Okay. As I mentioned before, you can watch this video on fast forward because I do go slowly with working with this iPad and this software. So you can just fast forward, or use the tool symbol. Click on the tool symbol and then increase the speed. Okay, so that is what I need to calculate. When I calculate that, I'll look at the answer in a second. I just want to show you all these problems are similar, right? The same problem. All that's going to change is what I've done in black here. You're just going to change this because everything else is the same, right? From question to question. So for the first case, here's my answer. I get this simplifies into here. So this is the confidence interval presented as a plus or minus or give or take, right? This is creating an interval in words, but you can actually be more precise and actually compute the limits of the interval. Okay, so here are the limits of the interval. It's a very tight interval with a standard deviation of 0.2. So it's between 63.61 and 64.91. If you have problems creating that, let me know, okay? So it's just a matter of doing the the arithmetic, adding it together. The next question is the same question actually. Calculate the confidence interval that would be accurate 19 times out of 20. Okay, so now we're getting to understand what in the world a confidence interval is. 19 times out of 20, if you do the math, 19 times out of 20 is actually 95%. So it's another way of saying create a 95% confidence interval. Okay, now it's going to be accurate. What do we mean accurate? 19 times out of 20. It means that this interval we created around the sample, not knowing what the true population mean is, around the sample mean we create an interval that captures 95% of the observations, right? But in fact, there's more to it than that. Okay, in the theory that we learned about the distribution of the sample mean, right? The sampling distribution of the sample mean, and it turns out that the confidence interval also is just one. So this confidence interval is one of many possible confidence intervals we could have computed, right? If we had a different sample, we would have a different confidence interval, right? So, in fact, and that's what I'm trying to explain here. So here is the first simple random sample. These are the values from the simple random sample A. I'll call it sample A. I would calculate the sample mean of those, and I could also create a confidence interval for those. Similarly then, for another simple random sample, call it B, I can collect the data, right, randomly, collect these observations. These might be similar, the same, different, completely different, and then from there calculate a sample mean. And from the sample mean, I can create the associated confidence interval. So in the same way, I have dot, dot, dot. In the same way, I can calculate, or I can create a set of all possible samples, all different combinations of the observations, which are drawn from the actual values. Then I can get the whole set of sample means, and I can get a whole set of confidence intervals. The idea of the confidence interval is that C% of the confidence intervals I create actually will contain the true population mean. Okay, and this is true for all the confidence interval. It will contain the true parameter, the actual parameter. So let's say this was an interval. So all the intervals are the same width, right? Because this is always the same. So if I make all confidence intervals of the same, if I make all my confidence intervals based on all possible samples the same C% level, so let's say for all of these I'm making, for example, Z star equals 1.96 because I'm making 95% confidence intervals. Then the width, the margin of error, the width of the interval will always be the same, right? So all that's going to change from sample to sample is this value, the sample means. So what's going to happen is the width will always be the same. So let's say that's the interval. That's the lower to the upper limit. The next one could be something like this. It's the same width, but it has a different center, a different sample mean, right? Because it was a different value. It could be the same, could be different. So this would be X bar A and this one would be X bar B. They're different, right? And then you can imagine I'm going to make more. I'm going to compute more of them. I could get one over here even. X bar C, right? And so what's going to happen is, imagine all possible samples, all possible intervals. So let's say there's even more. And then there's one here, same length. That's X bar D, okay? So out of all the possible samples and all possible confidence intervals, 95% of these, so if you have 100, 95% of them means 95 of them will actually cover and contain the actual mean, what we're trying to estimate. So it's basically not going to, it's like a risk of 5%. 5% of them will not have the true mean, and you don't know if yours is the one that is not going to have the mean, all right? So it's this is what we're using based on the theory. This is what we're using as an estimate. All right. It's not perfect. You need to know its limitations, but there it is. Okay, so you can rewind that if you didn't understand it, or you can continue. So part B is the same answer because 95% confidence is the same as saying that it's accurate 95 times out of 100 or 19 times out of 20. Okay, now calculate 99.7% and 99%. So you'll see in the answers, all I'm changing each time, if you look at your notes, all that changes is this number for the level of confidence. Otherwise, the numbers stay the same. So you just keep changing that number, okay? And even for C, all we did was change this number. So the larger the level of confidence, the larger the Z star, right? You're going to have a wider confidence interval. So the Z star is going to be higher. Okay? So I don't know what more I need to say about that. If you have any questions, hi Zelia. If you have any questions, let me know. I think that's for you to work on, but every time you solve a problem, contemplate what you're doing. Okay, so that is using the confidence interval. Oh, I wanted to show you in the table here. So you see, as I was saying, the greater the confidence, you see, what you're doing is you're making a wider confidence interval. So the Z star is higher because you're so many more standard deviations from the mean. So this is, you know, this is like 2.5 standard deviations from the mean. 99.7 is not on here, but this is 3 standard deviations after 99.8, 3 standard deviations from the mean. Right? So Z star is higher, the confidence level is higher. Let's see now. Let's go to the next formula. So this next formula is about sample size estimation. So let's say we want to, before we start a study, we need to collect a sample. We need to know what size sample we should collect. What size of the sample should we collect? So if we pre-specify the confidence level that we want for our estimator and the margin of error that we want, given in this row, we're given the true standard deviation, we can estimate the sample size. So you see, this is what you need in advance of a study to estimate the right sample size. And this is for a simple random sample. Okay, if you have a different kind of sample strategy, then it's similarly you would have to estimate, you know, with some sort of formula you could estimate the sample size, but this is how you do it for a simple random sample. In fact, I didn't mention it here, but in sampling theory there's a set of formulas. Now this is the more base formula, but there are a set of formulas that actually introduce a variable C into the calculations. C for cost, okay, because every sampling unit costs money. So if you want to also limit, or you want to take account of your cost, you're going to enter that into your formula. But I won't do that here. I keep it simple. You can take sampling theory and learn more about that. All right, so where does this formula come from? The formula comes from, remember, this is the margin of error, which I'm going to pre-specify. I'm going to set, prior to doing the sample, I'm going to set M, and I'm not going to put the number here yet, but I'm just going to preset it, and then solve, isolate N. So algebraically, to do that, I reverse these two, right? So in other words, I divide by M on both sides, and I multiply by square root of N on both sides. So that turns out to be just flipping these two. So you're going to have root of N equals Z star M. We're almost done. It's very fast. Then, to isolate N completely, N is equal to, zoom zoom, the Mazda formula. There you go. Okay, so that is the formula for sample size estimation when you want to estimate a sample mean. The M is not in it. Let me get that out. There. So let's use it. So I promise that I wouldn't give you on the quiz on Thursday. I'll just give a question up to what I do today. And I'm going to finish, the last thing I'm going to do is solve, I'm going to do a problem of one of these, and then I'm going to solve a problem in hypothesis testing. Let me know if your notes got mixed up in the transition to PDF because my notes are a little bit messy. Okay, so let's see. Oh, I had a question here. That you realize. Oh, okay, so here's the information from the question above. What sample size should you draw for a simple random sample to obtain a 99% confidence interval with a margin of error of m equals 1? Then then I change, what I do is I change m, and then here I change the z star. So it's just a play between the inputs, right, to the formula. I cannot change sigma. I can't do anything to sigma. That's just given to me. But I can make decisions about z star and n. If I increase z star, the level of confidence, the sample size must go up, right? Because if this goes up, then n goes up. If I increase m, however, the margin of error, let's talk about decreasing m. I want more precision. If I want more precision, I want a small margin, right? I want it to be accurate and tight. So let's say I make m even smaller. If I make m smaller, wanting more precision, that'll also increase n, okay? So more precision or more confidence, both of those increase n. So more precision or more confidence will effectively, more information, you gotta pay for it. You gotta get a higher sample, which costs more money. All right. So let me make that bigger so it's easier for me to write. More precision, decrease m, which increases n. If you want greater confidence of actually capturing the true population mean, that means increase the confidence level and the value z star, that will also increase n. Okay, so for more precision or greater confidence, you have to have a higher sample size. So I solve these here. Let's go through each one of them. So you can practice calculating it for yourselves. But if I plug this in, I get 35, right? And remember what I told you, it's 35.16, but because I want to maintain the precision of 1 as my margin of error, I don't want to exceed it, so I have to go all the way up, right? To keep m small, I have to add one more woman to my sample. And here I have the same level of confidence, but I want I'm going to be more relaxed. I'm going to allow a margin of error that's double. So I don't have to be so precise anymore. You see how much that affects it? I don't even need that many women. I just need 9. Actually, I won't circle that. So I have 8.79. I round that to 9. So look at the dramatic effect of not needing doubling the margin of error, less precision, less people. And then lastly, I'm going to work with this one, A and C. I'm going to allow the same level of precision So same degree of precision, 1 and 1, but I want a 95% confidence interval, not so confident as in an A, right? So that also from 36, it relaxes to 15.37, which I round to 16 women, all the way up to maintain my precision of 1. I hope you follow that. If you don't, rewind and listen to that, what I had to say there. So I made some statements here that you can read and realize if the impact of these variables, okay? Sigma you cannot change, but if you have information on sigma, always update to the best information that you have. The higher the confidence level, the more larger sample you need. The tighter, or more accurate the estimate, the smaller the n. Okay, so I don't know if you had a chance to read any of this, but let me do, we'll do the first one, and probably that's all I'll be able to do. All right, so here's a problem. The problem is that I have some data on executives and their blood pressure for a set of companies, okay, a bunch of companies. I have a sample size of, I do have a sample size. I have a sample size, so I'm not doing estimation of sample size. I'm doing a test of hypothesis. The sample size is 72. So with the sample, I want to determine if the executive's blood pressure, if executives are more stressed out than the general population. And I'm going to focus on males because their blood pressure is different from females. So I'm going to focus on male executives. And so the National Center of Health Statistics reports that the systolic blood pressure for males 35 to 44 years of age is normally distributed with a mean of 128 and a standard deviation is 15. So I have that information on the general population, and now I want to take executives around the same age, and I want to measure their blood pressure. Like, they all have to volunteer, of course. And I want to see, are they more stressed out? And is that calculating into their blood pressure? Or, well, anyway, you can think of different things, but I think that's really what I want to capture here. Can I see in their blood pressure that they're more prone to stress? So, I use this, so this is the setting. We're going to carry out the 5 HAPC steps, right? So the first thing to do is lay out H. H is the hypothesis test, which I'll make bigger. So it's always going to look like this, I told you. The null hypothesis, the alternative, a colon here, and a colon here. And I'm going to put the parameter. The parameter here is mu. An equal sign goes here, and whatever number I equate it to, I also put it in the alternative. And it's up to me to decide if this is less, greater than, or not equals to. Okay, now the number I put there is the first question, and then we'll deal with the sign. So since the status quo, without any additional information, is that what we know. What do we know? We know males have a blood pressure of 128, systolic blood pressure of 128, and we are going to presume executives are no different from the general population. Male executives are no different from the general populations of male around the same age. So they have presumably the status quo average. Whatever number I put there, I have to put here. And now, what are we looking for? Let's go back. Let's go back and read the problem and see what are we looking for. What is the test? What is the hypothesis? Claim. No, that's not it. I guess I put it here. Oh, there it is. Example 1. Is an executive's blood pressure different from the population of males? Different means it could be higher or could be lower. So without a sample to look at, I'm just going to use different. We're going to begin with not equals. Got it? So that's the H step where it's done. Next step. So let me write the letters again. Hap C, right? So A is the next step. A for assume. What do we assume? Well, we can't do anything unless we assume we know the population mean. So we're going to stick with the status quo. This is the status quo in the null hypothesis. What people tend to believe. We have no reason not to believe it. Let's see if we have evidence against it. So we're going to assume it's true. Assume H0 is true. So we assume that mu equals mu0, the hypothesized mean of 128. So thinking that that's true, then I don't like how the 8 turned out. Oh my goodness. Okay, it's going to have to stay. That's 128. All right, so then a sample mean, because of that, from the third row of the formula sheet, it is the case that the sample mean then is normal with a mean of the hypothesized mean and a standard deviation of sigma over square root of n. So let's read above for those values. What's sigma, what's square root of n? So if you remember the numbers, sample size of 72 was drawn, assuming that the sample was drawn from the population which is distributed normal. So remember, if we don't know it's normal but our sample size is large enough, we can assume, or we can approximate with the normal distribution. X bar would be approximately normal, but we're actually told that the blood pressures are normally distributed. Okay, so I'm going to take that number that I circled, the n, and I'm going to take this value, which is the actual population standard deviation, and I'm going to use it for the distribution of the statistic. So because of this, I know that this is 15 divided by square root of 72. And when you calculate that, so you should practice calculating that because it's not exactly straightforward. So make sure you can punch that in. And I get 1.77. Okay. So that is my second step done. Step 3 what do I do with this? I assess the evidence. I'm going to assess you're going to assess the evidence. The evidence was that in a sample, I have to go up again, in the sample that was taken, the sample mean from the sample was 126.07. So that's my evidence. I'm going to write it down here. I'll put it in red, the sample stuff. So it's 126.07, and the question is this different from the hypothesized mean of 128? Now these numbers are very similar, right? But depending on the deviations from the mean, it could be different. Okay, so if the standard deviation of x bar was really small, these could be different. But in this case, it doesn't look like they're going to be, right? So if you look here, this is the sample mean. The standard deviation is this value, right? So like within 2 standard deviations or even 3, you're going to catch this value. So they're going to be close together. So I have a sense that we're not going to find something special here. They're not going to be different, but we have to write it formally, you know, we have to write it out formally. So let's assess the evidence. The way we assess is we determine the number of standard deviations that our result is apart from the hypothesized mean. So I'm going to do this in black. So we're going to create, in doing this, a Z statistic, right? Because we know that, or we assumed that x bar was normally distributed. So we're going to take our result, 126.07, and we're going to standardize it with the mean and standard deviation. Now I'm calling it standard deviation again because I'm actually using the population parameters to calculate it. But anyway, but we should be calling it the standard error, I guess, because we used n. So 126.07 minus 128 divided by 1.77. Oh my goodness, look what I did. I just want to get rid of this stray line, but okay, fine. All right, that's the number. So punch that in, and you'll see that so 126.07 minus 128 equals divided by 1.77 gives you negative, so it is a negative, right, because it is smaller, so it's going to be negative, so it's going to be below the mean, but by just 1 standard deviation. To be more precise, it's 1.09 standard deviations below. What do I do with this? So this was the assess step. And now I am at the p-value. I'm going to convert this from standard deviations from the mean, so I know now that I'm not an outlier. This result was not an outlier. It's within reason of the, assuming that the mean was 128. The result we got was not strange. It's not an outlier result. And so now I'm going to convert it to p-values because that turns out to be the way that we conventionally like to present our data. So the next 2 steps are just for reporting, all right? But we pretty much have our answer now that we didn't find anything new. We have no evidence against the status quo, nothing special here. the test is not significant. Okay, so but let's write this up. So what's the p-value again? The p-value, I'm going to write it in words. I'm going to stop doing that soon, but for now, the p-value, what I'm going to do is make this a bit bigger. The p-value is the probability of seeing a z-stat as extreme or more extreme given H not true. I'm going to make this as short as possible. So what do I mean extreme or more extreme? What I'm saying, if you watch my other videos, is I'm saying, well, I know that the X bar came from a normal distribution, and then I standardize it, and I got the Z distribution, so I can use that and say, okay, well, let's plot it and see, is it an outlier? In fact, if I plot it here, I got negative 1.09, so it's here. And what is the associated probability, the tail probability of that? I have to look that up on my table and get the value. I have to get the value of negative 1.09 negative 1.09. Be careful with this. It's the last column, right? Of negative 1.0. So I get 13.79%. So the chance of seeing a sample mean that's one standard deviation below the actual assumed mean, or assumed actual mean, is 13%. So the chance of seeing that is 13%. But I'm not just going to check on that side, right? This is a two-sided test. On the two-sided test, it could have been also higher. So we got 1.09. The way that we do this is I check on both sides. So what's the chance of being as extreme or more extreme? The decision of where to look, which side to look on, is determined by the alternative hypothesis, right? The alternative had a not equal sign. That tells me to go on both sides. So it's 13.79 here, and it's also 13.79 here. So I have to actually add those together. So it's 2 times 13.79. It's 2 times 13.79, which is 27.58. So my result is a p-value .2758, and that's the p-value step. So just, you don't have to write out the wordy explanation of p-value, just make a drawing, identify where you're going to look for what, probability, the tail probability of your result. If it's not equals, then you have to check greater or smaller, so on both sides. If it's just, less than, then you just check on the left side. If it's greater, then you check on the right side. So now we're done with that. We're almost finished. Last step, and then I'm going to let you go. The last step is the C step, conclusion. Conclusion. And you have to remember this. P-value less than or equal to alpha means reject. So you have to remember this. Write it on your formula sheet. You get to use it. Reject H naught. Okay, so if this statement is true, you reject the null hypothesis. The p-value we already figured out. The p-value was 0. The p-value was 0.2758. Unless I specify a different level of significance, we always compare this to 5% because we're saying the chance of seeing the sample mean as one standard deviation below the mean or above the mean was 27, so about 30%. That was the chance. And for us, that's not strange. If something occurred when it had a chance of 30% of occurring, we say that's fine, that's acceptable, that's reasonable. So there's nothing wrong with our assumption. We failed to reject in this case as a result. So we don't have something new or something to report. In this case, the test is not significant. Okay, the test is not significant. Depending how you want to make your statement, I'm going to just make it in, well, I'm going to do two different ways. I'm going to say there is insufficient evidence to reject H naught. Okay, so but that's not so descriptive. Let's be more precise because I could say that anytime, right? So that's a statement I could make. Oops. The statement I could make in general, but that's good to know that. And this is also a general statement. But let's be more specific about this problem. What did we find out? We found out that there's no reason to believe executives have different blood pressure than male executives have different blood pressure than general population of males, okay? So you can write that down. You need to know all these ways of saying it because you might have a multiple choice problem and it might present the answer in alternative ways. So you would say there is insufficient evidence that male execs have a different blood pressure than males in general. And I didn't say anything about the age, but around the same age. I'm going to put that in brackets. Now you can see this nicely typed out in the notes, but there it is in a messy presentation. There is insufficient evidence that males execs have a different blood pressure than males in the general population around the same age. Okay, so that's it for today. Unless you guys have some questions, you guys can ask me. Otherwise, I'm gonna let you go. Okay, have a good night and see you tomorrow. The quiz will be up to this material, like not this example, but this material. Okay, so everything in formulas 1 through 5 I finished. You have to practice. The quiz will be on formulas 4 and 5. For the quiz inf. Okay, on Thursday. Okay, good night.